Hi, welcome to the exercise for the nucleophilic substitution. Okay, these are the exercises that you have in the worksheet in Blackboard, and this is the answer. Okay, basically the first exercise is to draw the arrows in order that the mechanisms have sense. They say that it's SN2. How it's working? Okay. First, we identify the nucleophile and the electrophile. Okay, the nucleophile will be where we have the negative charge. Okay, and what is happening is this pair of electrons of the oxygen attacks the carbon that is bonded with the leaving group, that is a halogen. Okay, because this is SN2, everything happens at the same time. The attack has to be dorsal, has to be from behind of the leaving group, and what we get is the final compound plus sodium bromide. Sodium and this bromide that will form the ionic bond. Here exactly the same, the sulfur is the nucleophile, will attack the carbon, the pair of electrons will be taken by the chloride, all is happening at the same time, all has a transition state. Okay, and what we get is this final product plus sodium chloride. And finally, exactly the same. Remember that the nitrogen has a pair of electrons. This pair of electrons will attack the carbon. Where is the bromide? The bromide will depart at the same time. Remember, transition state, etc. And what we get is this final compound. Okay, this is very easy. I didn't ask to draw any transition state. That means that only remember that all of these are going through a transition state because it's SN2. Okay? And we will have an inversion of the configuration in all the carbons. That in this case we don't care so much because all the carbons are achiral, are not asymmetric. Okay? Understood? Good, we go for the second one, for the second exercise. In the second exercise, what we are doing is they say us that we have this reaction. And they ask us to draw the mechanism. And they say that it's SN1. It is necessary that they say that it's SN1. Well, not so much. Why? Because basically, if you take a look, you know to differentiate SN1 of SN2, you only have to check the carbon where is attached the bromide, or at least it's the first thing that you have to do. In this case, we have a tertiary. That means a tertiary carbon stabilizes very well the carbocation, and if we want to approach a nucleophile here, as you can see, we will crash with everything. Okay? That means it will be difficult to approach a nucleophile to this position, and will be easy to stabilize a carbocation. That means that everything is favoring the SN1 and everything is disfavoring the SN2. But where we go, first step, if it's a SN1, the leaving group is departing, and what we generate is a carbocation. Okay, this is an intermediate, not a transition state, it's an intermediate. Okay? And then simply what is happening, the nucleophile is coming, in this case the iodide is coming and simply will attack the carbocation to form the bond between the carbon and the nucleophile, in this case the iodide. Okay? Second example, we have this compound. again, must be SN1 for the same reasons that we said before. Okay, in the case that I didn't tell you if it's SN1 or SN2, has to be SN1 because basically it's very crowded, it's a tertiary, and stabilizes very well the carbocation. Okay, first step, the leaving group is departing. But what's the problem? We have an OH as a leaving group. The OH is very bad leaving group, cannot live alone. What we need to do is to transform this OH in a group that can live. That means that basically we add hydrobromic acid, the OH will attack the acid, and we will form this compound. Okay, we only protonate the alcohol, and now the leaving group is not anymore a hydroxyl, the leaving group is a water, and water is a very good leaving group, that means that we will leave, and we will form now, yes, the carbocation. When we form the carbocation, the nucleophile, that in this case is the bromide, will attack, and what we will have is the final compound. Okay? What is the importance or the trick here is that you need to protonate the OH. You need to remember that the OH is a very bad leaving group, and you need to protonate it in order that make possible the departure of the oxygen, okay? In this case, in the form of water. And the last one. In the last one, they say that we are doing a reaction that is going through a SN2. Oops. We add cyanide to this compound, and what we get is what we have to answer. Okay? First of all, we need to identify the nucleophile and the electrophile. The cyanide will be the nucleophile, and this will be the electrophile because we have the leaving group attached to the carbon. Okay, in this case a chloride. SN2, what we need to remember that the SN2 has a transition state, and the attack of the nucleophile takes place by the opposite direction where is the chloride. Okay, that means that we have to draw this with the chloride in one side. Okay, and then be careful, we have to put these things in order okay, and then the nucleophile is attacking from behind. In this case, the cyanide is attacking from behind of the chloride. We are forming this bond at the same time that we are breaking this bond. Okay, we are forming the cyanide carbon bond at the same time that we are breaking the carbon chloride bond. Why I put this in this way? Okay, because this stereocenter is determined by the stereocenter of the starting material. If I put the chloride looking in this direction and the metal going down, the ester is coming in front of the slide and the hydrogen is coming behind of the slide. If you don't see it, that is normal because you are in the first year and this is difficult, use molecular models. Okay? In the exam, well, this year doesn't care, but always you will be able to provide molecular models to the exam or to any test. Okay? That means use it, get used to to move the molecular models because are very, very, very useful. Okay? If you do it, you will see that if you put the chloride in this direction and the metal down, the ester is coming to you and the hydrogen is coming inside. And what is happening simply is that what we get is the cyanide we got the inversion. The chloride was in this position and now the cyanide is in the opposite position. If we do, which is the stereochemical descriptor of this compound is 1, 2, 3, has to be S. Please, if you don't see it, I did it very fast because basically, well, I have quite a lot of experience doing it, and I hope that I am not getting wrong, but I don't think so. Use molecular models, and remember the rules in order to determine if this stereocenter is S or R. Okay, if we do it this, we have 1, 2, 3 is also S. And then you can be surprised. You say, oh, you say to us that in SN2 we always have an inversion of configuration. And yes, this configuration is the inversion of the chloride. Then why is not R? Because the Ingold-Prelog rules are rules made by us. And the problem is that here the chloride is the atom or the substituent with the bigger preference because it's chloride. However, in this other compound, cyanide only have preference 2. The first preference is for the ester. Okay? That means we have an inversion of configuration. That doesn't mean that we change S for R, S for R. Sorry. That is the most normal that happens, that we start with S, if we do SN2, we get an R. Yes, it's the most normal, but not always. You have to check the starting material and the final compound always. Okay? You cannot assume that the S is converted with R, because there are some times that this is not happening like this. Okay? Well, these are the exercise. Thank you very much for your attention, and see you next week with the exercise for the elimination. Take care.